All right, 8th graders, this is the walkthrough for Physical Science Station 1. You should have been given a packet on Friday by your 8th grade science teacher, either Ms. Munnerlin, Mr. Kulikowski, or myself, Mr. Young. You need to get that packet out, and you need to open it up to the first page, which is Station 1. And the first part of Station 1 is boiling water. In this example, we have a hot plate that's heating up some liquid water, and at the top you can see it coming out as steam. That is gaseous water. Now, water of any form has the chemical makeup of H2O. It's made up of 2 atoms of hydrogen and 1 atom of oxygen. Regardless of if it's a liquid, if it's a gas, or if it's in solid form, which you guys know as ice, it's always going to be made up of H2O. In fact, you can go back and forth between the phases. You can go from steam back to a liquid in a process called condensation. It's what happens with clouds. It's also what happens on your cold sodas when you take them out of the refrigerator. The reason that that liquid forms on the outside is because there is water vapor in the air. When that cools down, it goes from steam or water vapor back into liquid water. You can turn liquid water back into ice by a process called freezing. And then you can go forward, take ice, turn it into water, that's melting, take water, turn it into steam, and that is boiling. This is a reversible change. You can boil all of that water off, turn it to steam. If you collect it all, you can get every single drop of that back by cooling it off and condensing that liquid. Physical changes can be changed back. A phase change, which is what this is a physical change. A chemical change is where you change the chemical makeup. So it would no longer be H2O. It would be something else. But in this case, regardless of if it's ice, water, or steam, you always have H2O. I hope that helps you finish all of the questions on Station 1, Part 1. The next part of the video is going to address electrolysis, which is the chemical splitting of water into hydrogen and oxygen atoms. All right, Freedom, this is the second part of Station 1. This is an electrolysis apparatus. It's a 9-volt battery where the wires are connected to pencils that are immersed in the water. This isn't just normal water. This is water with a little bit of sulfuric acid. The sulfuric acid is an electrolyte. Those of you that drink a lot of sports drinks like Gatorade, you know what an electrolyte is. But in this case, an electrolyte allows electricity to be conducted from one side of the reaction to the other. So you've got electricity going from the black wire to the red wire. Now, in the case of the battery, the black wire is negative and the red wire is positive. Over here, you've got one side that's got big bubbles and one side that's got little tiny bubbles. The side with the little tiny bubbles is the hydrogen. The side with the really big bubbles is oxygen. Because what's happening in here is the electricity is tearing water apart. And you're taking that water molecule, which is made up of 1 oxygen and 2 hydrogens, and you're using electricity to split it into molecules of oxygen and molecules of hydrogen. Oxygen loves to bond together, so you wind up with O2, but for every 1 O2 molecule, you have to rip apart 2 water molecules, so you get 1 molecule of O2 and 4 molecules of the hydrogen. So on the hydrogen side, it's going to fill up twice as quick because you are removing twice as many atoms on that side as you are on the other side. So the big bubbles are the oxygen, the small bubbles are the hydrogen. Hydrogen is being broken apart by the positive end of the reaction. Oxygen molecules are being broken apart by the negative end of the reaction. All right. I believe that's everything that you need to be able to answer the second section of Station 1. All right, Freedom, this is Station 2. This is the station where you have Sean doing an experiment In this experiment, he purchased 3 t-shirts that were all white. They were made of different materials though, and he tested them with a UV meter to see which ones would block ultraviolet light better. In order for Sean's experiment to be valid, he had to make sure that he was only changing one variable. In this case, it was the material that the t-shirt was made of. So all of the other variables, the color, the size, the amount of sunlight, they all had to remain the same or the experiment would be invalid. For this experiment, Sean put a UV meter under each of the t-shirts and put them in the same place so they received the same amount of sunlight. He also had a 4th meter that was left uncovered so that he could get a baseline of how much sunlight was coming down, how much ultraviolet radiation was hitting the area. The results of Sean's experiment showed that the uncovered meter registered 66% UV coverage. The Kmart t-shirt, the cheaper t-shirt, registered 16, so it brought it down 50%. The Old Navy registered at 6, and the Abercrombie, which was the most expensive shirt, registered at 3. So there was a decrease in the amount of UV exposure in the more expensive shirt, but I don't know if it equated back to the cost. In other words, I don't know if the great increase in cost is worth it to get a 3% drop between the Old Navy. One thing that Sean can conclude, though, is that all of the shirts blocked ultraviolet radiation, so they all had some properties of blocking UV. All right, everyone, this is your walkthrough for Station 3 on measuring density. So for part 1, I've got these 3 cubes. I've got iron, which is black. I've got aluminum, which is a silver color, and then I've got, this is pine. If you know what a pine tree is, then that's what this is. And it's kind of a tan color. And what we're going to do is we're going to put them on this scale. Now they are all the same volume, and if you look at your paper, it tells you that the volume of all the blocks is 16.46 cubic centimeters. So they're all the same size. We're going to take this block, we're going to put it on the scale, and that's the mass, 129 grams. That's for the iron, the black cube. Then we put the silver cube on, the aluminum, and even though it's the same size, we see that it's only 43.8 grams. So we take that one off, and now we go to the wood. And even though the wood is still the same size as these two, it is much lighter. It is only 6.7 grams. Now, you know the volume because it was reported on your sheet. We just figured out the mass. In order to find the density of those 3 cubes, we use this formula. This is the formula for density. We take the mass that we found using the digital scale, and we divide it by the volume, which you know because it tells you on your sheet, the volume is 16.46 cubic centimeters. Volume could either be milliliters if it's a liquid, or it could be cubic centimeters. Now the cool thing about these two is, if you had a box that was exactly 1 cubic centimeter, and you filled it up with a liquid, that would equate exactly 1 milliliter. So 1 milliliter is exactly equal to 1 cubic centimeter. So the way the metric system works, you can easily jump back and forth between liquid and solid measurement. So on your paper, in order to find the density of the 3 materials, you're going to have to take the mass that we found on the scale and divide it by the volume of each of the 3 cubes. Then you will be able to answer the 2 questions on which of the cubes has the lowest density and which of the cubes has the highest density. Now to help you answer the question number 4, I have a bathtub, well, a container filled with water, and it says that water has a density of 1 gram per milliliter. Remember, a milliliter is exactly equal to a cubic centimeter. So which of these cubes are going to float in water? All right, well, I'll tell you right now, if any of the cubes have a density that is lower than 1.0, it is going to float. So we'll check that right now. The iron, if you did your math right, then you should have found that its density is higher than water. So if it's higher than water, I want you to predict right now if it's going to float or if it's going to sink. All right. Those of you that said sink, you are correct. The density of aluminum. When you did your calculation, you should have found a number. If it's higher than 1, it's going to sink. If it's lower than 1, it's going to float. It should have been higher than 1. And lastly, we have this cube. This is the wood, the pine. If it's higher than 1, it should sink, or it should, yeah, if it's higher than 1, it should sink. If it's lower than 1, it should float. And it floats. All right. Take my 3 density cubes out of the water. Now, the paper crumble. I've got 2 pieces of notebook paper. They are identical in mass, and in fact, they were identical in shape until just a few minutes ago when I crumbled this one up. This one takes up a lot less space. It is the same piece of paper, but it takes up a lot less space. If you take a look at your formula, you are dividing by the volume. If the volume of that balled up piece of paper is smaller, then you are dividing by a smaller number, which means the density is going to be higher. So because this takes up a smaller space, but still maintains the same mass, so for example, let's say it has a mass of 5 grams, like it tells you on your paper, and I was able to crumble this up so that it's only taking up 2 cubic centimeters of space, that means that its density is going to be 2.5. If this piece of paper takes up a volume of 5 cubic centimeters, then that means you're taking 5 grams and dividing it by 5 cubic centimeters, which means the density of the regular sheet of paper would be 1 gram per cubic centimeter. So by crumbling something up or by making it smaller to take up smaller space, then you are decreasing the volume, keeping the mass the same, which makes the density higher. If you keep the mass the same but make it take up a smaller space, you are increasing density. And that happens because inside, in a low density object, the atoms are spaced a little bit apart. They're still packed because it's a solid, but there's a little bit of space in between them, so there's not as much matter packed into the same space. In a high density, everything is so tightly packed that there's hardly any room at all. The more the density, the higher the density, the more tightly packed the atoms are. So for low density objects, not as tightly packed. For high density objects, very tightly packed. All right, and then the last question talks about a marble and a cruise ship. Now, previously, I put that aluminum cube in the water and it sank. But here's my aluminum boat. Now, aluminum has the same density. In order to be called aluminum, it has to have the same density regardless of its size. In this case, though, I've made it into a shape where it's not just aluminum. If I were to measure the height, the length, and the width, I would find that this is filled with mostly air and a thin layer of aluminum on the outside. And because of that, the mass is going to be much smaller. If my scale will turn on, there we go. The mass is going to be much smaller. Even though this takes up a lot more space than the cube, the mass is a lot smaller than the cube. So what winds up happening is when you can spread your material out, it floats. This is why cruise ships float. You take an iron cruise ship made out of this stuff, you spread the iron out, you fill it with mostly air, and you create something that has a density that is less than water. So instead of sinking, it floats. When you poke a hole in the boat, it fills up with water, its density is no longer less than 1, the boat sinks. A marble is tightly packed glass molecules. When you drop them in, sure enough, it sinks. But if you were to take that marble on a cruise ship, it would float. Because the cruise ship has a density that is so low, you can add extra weight. You can add luggage, you can add people, you can add food, you can add a hydro slide, you can add putt-putt golf, you can have DJs doing dance parties, you can have pretty much anything that you want on a cruise ship as long as you do not exceed its weight limit and make its density higher than 1, in which case it would sink. But for the most part, cruise ships don't have to worry about that because their density is so refined that you can load it up with a lot of weight and a lot of people and it still won't sink. Just like an aircraft carrier. You can put F-16s, F-14 Tomcats, you can put F-18s, you can put AWACS, you can put a whole ton of airplanes on an aircraft carrier and it will not sink. But the second that you increase its density past 1, that aircraft carrier sinks. So here is my aluminum boat sinking because I poked a hole in it, it filled with water, and now it's on the bottom of the ocean.